Hi, I'm Andrew, and for my final year engineering project, I have taken on the challenge of being able to move a robotic hand and arm using the body's physiological signals. Human-computer interface is the ability to control and interact with the computer system using biological signaling. Signals that this project investigates are electromyography and electroencephalography signals. Electromyography, or EMG signals, records muscle activity. It can do this by placing electrodes along the muscle length, and as the muscle contracts, a burst of electrical activity is created and seen. Electroencephalography, or EEG signals, measures the brain's activity. Using EEG signals to control a computer is coined as a brain-computer interface, or BCI. The use of such technology as it grows can be widespread, from simple tasks such as turning on and off a light to something seen in a futuristic sci-fi film. This project aims to focus on the possible uses this technology could have for those who are disabled. The work here looks to be able to improve the quality of life of those who are amputees and those who are immobile. The number of amputees in America is estimated to be 2.9 million people, with a fifth of those being upper limb amputations. This project looks at the control of robotics using EMG signals. To be able to do this, a dataset must be obtained. This dataset is made up of recordings of the subject doing repetitive tasks such as different finger positions and elbow positions, where EMG signals are recorded using electrodes that are placed over the active muscles. The project also looked to decode imaginary left and right-handed movement from the EEG recordings. This is for one-dimensional control. Imaginary movement is where the subject imagines moving the hand without any physical movement. Features are then extracted from the recorded signals. These features were from the time and frequency domain and are needed to be able to discriminate between the different positions that make up the dataset. The feature sets were used to train a supervised machine learning classifier, such as linear discriminant analysis and support vector machine classification algorithms. The goal of this project was to have a real-time testing of the classifier's performance and to use the classifier's output to move the robotic hand or arm. Using half-a-second time windows to determine the position of the body, using the EMG signals, an accuracy of 98.8% was seen in real time for the 3 different elbow positions, and 78% for the 7 different hand positions. For EEG signals, an initial step of being able to move the cursor left or right was set up. While offline classification results were up to 80%, this was not seen in real-time recording results, which were at random. I'd first like to give you a bit of background information on the equipment that I used for my project here in the Neurobotics lab at Monash University. The lab had purchased an Open EFIS acquisition system, which is a multi-channel system, and that is being fed by these amplifiers here. We can connect to these amplifiers with an EEG cap and EMG electrodes by custom-made connectors that I've made here.
Here is the UR5 Universal Robot and Open Bionics Brunel hand. These will be used to demonstrate the output of the classifier.
Here is the project outline. The goals of the project are the control of a robotic hand and arm by measuring EMG signals from the bicep and forearm muscles, and one-dimensional control from EEG signals. First, we need to acquire the signal. The electrode positions need to be decided for both the EMG and EEG signals, and are connected to the Open EFIS system. The concern in this area is the signal-to-noise ratio. EMG and EEG signals are very small, in the order of microvolts, and can be easily be hidden by background noise. This will need to be addressed. Finally, the positions and movements will need to be recorded. Next, we have feature extraction. Once the signals have been recorded, we need to organize it into separate channels and positions for which it represents. Next, the features of each position need to be found. Training of the classifier. As we know the true state that each of the feature sets belong to, we can train a classifier. The accuracy of different feature sets can then be explored. Real-time classification. Choosing the best classifier, we can then adjust the program to connect to the robotic arm and hand. The arm and hand position can then be made to represent the position the person is currently in, and processing techniques of the classifier can be looked at to reduce any errors from being outputted.
For the classification of finger movements, two muscles have been chosen to record signals from. These are the flexor digitorum muscle, which flexes the fingers, and the extensor digitorum muscle, which extends the fingers. For classification of elbow position, the biceps brachii muscle was recorded over. Silver chloride electrodes were used. They would be placed longitudinally along the muscle. 2 electrodes are required to be placed along the muscle, with one of them being the amplifier's reference electrode. For EEG, 9 electrodes were chosen to record from. These electrodes are positioned above the motor cortex and supplementary motor area. Prior research has shown that these areas are activated in imaginary movement in a similar fashion to if the person were to carry out the action. The electrode cap is worn by the subject, and each electrode that is used is filled with electrolyte gel. Before you is the background noise that is seen when first connecting the EMG electrodes onto the forearm, with an amplitude close to 6 mV. Additional electrode gel was used to try and reduce the electrode impedance, and reduction in noise was seen. Having the ground and reference inputs of the amplifier separated showed the greatest reduction in noise. And here again with the axis was scaled. Connecting the cable shields to ground showed a slight reduction. In total, the reduction on the background noise RMS value was 99.7%.
Now that the signal-to-noise ratio has been improved, data from each position that is going to be classified needs to be recorded. Experiments are run through a MATLAB toolbox called NeuroStim, which allows for the creation of repeatable experiments. An experiment is made up of trials for each position that is being tested.
A trial for EMG is shown here. The subject is signaled to move to the new position and hold this position for 4 seconds. The 7 finger positions that are used are shown here, with individual finger flexions and open and closed hand. 3 elbow positions were also tested for. EEG trials were made up of a fixation point before the condition of left and right was signalled.
Now that we have captured the data, we must now process it. Features must be extracted for each trial.
Features are found to be able to distinguish between EMG signals of different positions. Features can be from the time or frequency domain. The time domain features used were the mean absolute value, the variance, the waveform length, the number of zero crossings, the number of slope silence changes, and the autoregressive filter coefficients. This is where we model the signal as an autoregressive filter and use the coefficients of the model as features. The frequency domain features used was the average power of 20 Hz frequency bands. For example, the average power between 0 and 20 Hz, 20 to 40 Hz, all the way up to 480 to 500 Hz. This figure here shows the FFT response of the average signal for each of the 3 elbow positions. We can see that the FFT response is distinguishable between the 3 positions. For EEG feature extraction, a common spatial pattern filter was created from the trial data. A common spatial filter is designed to transform the channel data, which can be seen here by 2 different channels in the 2 different colours, so that it has a high variance for one condition and a low variance for the other condition. Then the other channel can have a high variance for the second condition, but a low variance for the first condition. We can then directly use the variances of the different channels as features to be used for the classifier.
From EMG trials, the data from the holding state was separated into half-second blocks, and with the shifting window, a total of 714 feature blocks to train the elbow classifier, and 2,674 half-second feature blocks for the 7-finger position classifier were created.
Features were separated into 3 categories, being the time domain, frequency domain, and the autoregressive filter coefficients. They were used to train two supervised machine learning classifiers, which were the linear discriminant analysis and support vector machine. Here is a visualization of what an LDA classifier does. Here we're using two features, two autoregressive coefficients, to divide the three classifications of elbow position. Here the LDA uses boundary conditions to decide where the feature sets belong, if they're in the 0 degrees, 90 degrees, or 150 degree classes. Results are from the classifier using five-fold cross-validation, where 80% of the data is used for training and 20% is used for testing. We can see that all the features using the SVM classifier had an accuracy over 99% for the three elbow positions, up to 99.7%. Looking at the hand position accuracy, the time domain features, including the autoregressive coefficients, had an accuracy of 90.1%.
For EEG, 60 trials for each imaginary movement was recorded. The 4 seconds from each trial of imaginary movement were used for creating the common spatial pattern filter. Using this data, an accuracy of 78.3% for an SVM classifier and 80.8% for an LDA classifier was found. This is better than at random, which would be at 50%. Choosing the time domain features, including the autoregressive features, a classifier was used for real-time processing of the signal.
This resulted in an accuracy of 78% for the 7 hand positions. The classifier had difficulty in processing between the middle and small fingers. The elbow position had a real-time classification of 98.8%. Having only 3 states, this was accurately classified by a single EMG channel. The classification of both hand and arm position was then put together. In this demonstration, a more simple hand classification using 3 positions was implemented, and demonstrates how classifiers can work in tandem to achieve a goal. This is what would be required in practical applications. In testing the real-time results of the imaginary left and right-handed prediction, a program was designed to move the cursor depending on the classifier output. Results showed that the prediction favoured the right, and gathering a larger dataset as well as reducing noise would be the next step in improving on this result. This program would be useful as it gives live feedback to the subject and could help in their training.
The aim of this project was to acquire EMG and EEG signals, classify these signals, and use these results to move a robotic hand and arm, or move a spot left and right on the screen, in real time. In doing this, a successful experimental workflow in MATLAB using the NeuroSim software was completed. Experiments could be designed and data collected in a way that allowed for the subsequent data segmenting and feature extraction to be automated. This project has shown me the challenges of working with small electrophysiological signals in the noisy environment which we are surrounded by. I believe that this project has built the key building blocks that are required to be able to control a practical prosthetic in the future here at Monash.